So today we will learn complexity and recursion and various examples like Fibonacci and integer multiplication, power of large number, okay, and many more examples. And we will see how the complexity works. Okay, so let's start with the complexity. First, we will learn asymptotic complexity. Suppose we have a problem P. Okay, P may be any problem. For example, let's assume that we are given a number. We are given our phone number. We want to check whether it is prime or not. Okay, and that problem is named as P. I'm not writing the whole problem. Any problem like this is now I ask the student to solve this problem, write an algorithm or write a program to solve this problem. So the student will write a different version of the program. Let's say the student uh, one has written an algorithm or program, say A1, and the second student written A2. Okay, who will get more marks? Which algorithm is more better? Okay, so given two numbers, we can compare whether which number is bigger, which number is less. Why? Because set of all natural numbers, it is well ordered. Well ordered means you can compare the number. Okay. And to compare the number, we use symbols. What are those symbols? In the set of real natural numbers, there is greater than, less than, greater than equal to, less than equal to, and equal to. So how many such symbols are there? 1, 2, 3, 4, 5. Okay. So given 5 symbol, we can compare any two instance of the set. Okay. Why? Because set of all natural numbers is well ordered. Okay. They have the ordering, and that ordering is defined through the symbols. Given any two arbitrary number, for example 5 and 7, we can say 5 is less than 7. And uh, this symbol is giving the meaning of this notation. Okay, everyone understand that 5 is less than 7. 7 is the bigger number, 5 is this. But now consider we have set of all algorithms. Okay, for the same problem P, we have a set that contains all the algorithm A1, A2, A3. We can say algorithm, we can say program. Okay, that is synonymous. Okay. So let's say we have k number of students and we got k different solution for the same problem. Now which solution is better? Can we compare the algorithm? We have to devise some method. Everyone is thinking like that. We have to devise some method. Should we compare based on the number of lines inside the code? No, not at all. Efficiency. Okay. Which algorithm is more efficient? Efficient means taking less time. Okay. Now let's say I have given 7 as input and I have to check whether this is prime or not. I guess all this algorithm will work very nicely. Okay. All this algorithm will work very nicely to verify that 7 is a prime. So how we will measure which algorithm is better? Okay. This term plays the crucial. Okay, asymptotic. So the idea is we will not compare the algorithm on small input because given the computer hardware availability of the current day, we are computing for 7, it will take 0 seconds. Okay, no or no time at all. Okay. So we are not bothered about that at all. What we are bothered about, given the large number, for example, phone number, okay, your mobile number. So 10-digit number or more. Let's say 2048-bit number is not very large. Okay, in cryptography, every time you give some password, that get encrypted with some very large number, and there are a lot of functions, and those functions look for 2048-bit prime numbers. Okay, so you will compute that thing after few class, those algorithms. So given the number of very large scale, which algorithm is better? That is our concept. Among all these algorithms, we will give as large as possible input and we will verify which algorithm is running faster. Okay, that is a better algorithm. Okay. So we have two algorithm AI and AJ. Suppose for very large number, AI is performing more better than AJ. So we need some symbol, should we like less than equal to or strictly less than? No. Why? Because it has this symbol has some meaning. Strictly less than, strictly greater than, they are not devised to compare the algorithm. So when we are comparing algorithm, we need to devise some other symbol. So what are those symbols? We will use some other symbol and we have big O, small o, big omega, small omega, and theta. How many of them? 1, 2, 3, 4, 5. Why 5? Because we need 5. We have seen we need 5. And you can resemble the thing in a similar way. Big O is like this one, less than equal to. Okay, big omega is like greater than equal to, and theta is like equal to, and omega is like this uh, strictly greater than, and small o is like strictly less. They are not same, but for the understanding, you can map this thing. Okay. Now, giving two algorithm, they have some complexity. Okay, complexity means we have computed how many instructions are there, and if we run the full algorithm considering the loop or recursion, how many total number of time it will be. Let us assume that the input size is n and the complexity of this AI algorithm is fn, and that will be, if input size is n, the total time taken will be some function of n. Let's say that is fn. And the same thing for the second algorithm is, let's say, gn. Okay. So which one is better? We will say there is a definition. First, let me write the definition of big O. Definition of big O. You can spell it like big O, but I am using symbol. We will say Fn is big O of Gn if there exists, you know the symbol, reverse E. Okay, we call it there exist. If there exists a natural number n0, natural, since it is natural number, so let's like write in this way. This is set of all natural number n0 belongs to this symbol is belongs to. Okay, so there exists a natural number. It may be sufficiently large, but it is fixed, it cannot vary. Okay, sufficiently large fixed natural number n0 belongs to n such that, okay, we need one more thing, and a constant c greater than 0. Okay, if we have some positive number, fixed positive number, fixed natural number, and some constant c. C is a real number, and only condition is c must be positive. It should be greater than 0, nothing else. Okay, if there exists n0 and c such that fn is less than equal to c into gn for all, you know the symbol. Okay, convert of a, and we call it for all. So fn less than equal to c into gn for all n greater than equal to ng. Now this n is the variable. Okay, this n is the variable and this n0 is fixed. So what we are bothered about? Let's see once again the definition of BIGO. We have two functions fn and gn. We will say fn is BIGO of gn if there exists n0 belongs to n and c greater than 0 positive constant such that fn less than equal to c into gn for all n greater than n. Okay, so this n0 you can assume sufficiently large number, and as I told, we don't bother about the time taken by two algorithm when the input size is less than n0. Okay, if the input size is greater than n0, then only we bother. Okay, when input size is greater than n0, then we will check whether fn is less than equal to gn or not. Why we have used this c? This is basically a scaling factor. Okay, so we are only bothered about the behavior of the card, not the scaling of the card. Okay. Whatever the scaling, you can take any constant and multiply it. The curve will be shifted little bit. Okay, it will not change. So fn will be less than equal to c into gn, and we will say fn is BIGO of gn. Okay, means the complexity of gn is larger for all the input n greater than ng. Now you can make more definition. Similarly, we can write the definition of big omega, and what we have to do, we have to reverse this symbol. Okay, here this is less than equal to, we will take greater than equal to, and we have to check both the function that must be positive. Okay, it is written in many old book, but I don't understand why to bother about this. If it is a complexity time taken by some function, so that will be always positive. Time taken by some algorithm cannot be negative. Okay, so fn is same to gn. That is fine. So for omega, we'll change the symbol to less than equal to, sorry, greater than equal to, and for this small o, we will remove this equal to. Small omega will remove the equal to of the big omega. Now, what is theta? Theta don't have its own definition. If you have to prove theta, then you have to prove that the two functions are big O as well as big O. If you prove that, then they hold the theta. Okay. So what you have to do? Suppose you are given two functions, let's say 5n square plus 2n plus 3, and second function gn is n square. What, and you are asked what is the order relation between them. So what you have to prove? You have to prove, suppose you want to prove big O. Okay, so you have to prove big O, you have to find out some constant, fixed constant n0, and some positive number c, and you have to show this condition is satisfied when n greater than n0. Okay, for the example I just told, one polynomial is n square, another one is directly n square. So that will be actually in theta relation. So for that you have to prove this big O part and as well as big omega part. If you put both the part, you can say they are in connected within theta relation. Okay, means their complexity is almost equal. So in next lecture, we will use this complexity and notation for various problems.